Good morning everyone. So today onwards we are going to start our numerical analysis syllabus. So in this we have our unit 1 approximation of functions. So first of all, let's have a rough idea about what we are going to study in this unit. So basically you will be given some data. It might be in the form of set of points or particularly a function. So set of points, that means if x and f of x, or a function like x cube, x square, or so on. So if you see graphically, then what we have is, if you have x coordinate and y, that means f of x, right? So if you are given certain points, then what we have to do is we have to find a curve or a line depending on the question, so as the points are best fitted into this curve. So our work is to fit the curve in the given data. So in the process of finding the best fitting curve, you will have to find the solution for the minimization of error. That means you have to find a solution which has minimum error. Now error in terms of data fitting is what? So it is the difference between the observed value or the given value and the value of the curve which we find. Okay, so there are certain values which are given, for example x, f of x, and we have to find a curve, so there will be a difference between both of these points. So what we have to do is we have to find a solution so as the error is minimum as possible. Okay, so in this unit, we are going to use the best process of data fitting. So data fitting is just data is given and you have to fix one function, that is a curve or a line. So best process for data fitting is nothing but the least square approximation method. So this approximation is used to approximate a function f of x. Okay, that function f of x might be given in tabular form or it might be given explicitly, that means in the form of x cube, x square as such. Okay, so now in this case what we are going to use is the L2 norm. So what is L2 norm? It is nothing but square norm whose value is given by mod of x equals to square root of summation I running from 1 to n xi square. Okay, so this is your L2 norm and we are going to use this L2 norm in this approximation. Now the best approximation is least square because the error is minimized with the help of square value. That means if you have an approximation function, so what's the approximation function we have? We have already studied this function in your previous standard. So approximation function is given by c0 phi0 plus c1 phi1 up to so on plus cn phi n. Okay, so this is known as approximation function, and what we are going to do is we have to determine this constant c0 c1 up to so on cn, and the aggregate of w of x e square over a domain D is as small as possible because we have to find the minimum deviation. Okay, so now whatever the value of w of x e square is over a certain domain of the given data, we have to find the smallest possible value. Okay, and E is what? E is error of approximation, and W of x is nothing but the weight function. Okay, so W of x is a weight function. It is always greater than 0. If it is given in your problem, then you have to consider that weight. Otherwise, you have to consider W of x to be 1. Okay, now what is the error? So to calculate this error E, we have a formula which is mod of f of x minus p of x. Okay, so f of x is the function which we have to do, and approximate function, so f of x is the function given, and approximation function is, we know that approximation function is given by c naught phi naught plus c1 phi 1 plus up to so on cn phi n. Okay, so error is found between the difference of the given data of the function and the approximated function which we need to find. Okay, so we need to minimize this error. So to find, we find what the error, square of the error, that is mod of e square, so that the square should be minimum as possible. Okay, so as I've told you before, there are two ways in which data is given. The first one is discrete data. That means points will be given. Okay, so it might be x0, x1 up to so on xn. So in total there will be n plus 1 points. Okay, so in such case, what is the condition for IC0, C1 up to so on Cn? So IC0, C1, Cn is given by summation k running from 0 to n w of xk f of xk minus summation I running from 0 to n ci phi I xk and whole square. Okay, so this is in terms of discrete data, and it should be minimum. Okay, so this function should be minimum. It is the condition for discrete data. So this is our equation 1. Okay, now when it comes with respect to the continuous function, so for the function which are for the functions which are continuous on close interval a comma b, and they are given explicitly, we have the formula as I c0 c1 up to so on cn, which is equal to, now in this there was summation. When it comes on continuous function, summation is replaced by integration. So integration from a to b, where these limits are from the interval, so a to b, w of x f of x minus summation I running from 0 to n ci phi I x whole square dx. Okay, so this also condition should be minimum. Okay, so these are the two conditions, and when we will see the examples, it will be easy for you to understand. So now whenever the work function is given, you have to, that is this w of x. Okay, so whenever it is given weight function, then w of x is a weight function. So if it is given, if the value of this weight function is given, we have to consider that value. Otherwise, we have to consider w of x as 1. Okay, now what is the necessary condition for this both equation to have minimum value? So what we have to do is we have to take partial derivative of I with respect to every ci, okay, and it should be equated to 0. So whatever the equation is formed here, we have to take partial derivative of that equation with respect to each ci, and I goes from 0 up to so on n. Okay, so because of this, what we are getting is there will be n plus 1 linear equations. Okay, so there will be a system of linear equations, and there will be n plus 1 unknowns, that are c0, c1 up to so on cn. Okay, now whatever the equations are formed because of this, because of each partial derivative of ci, these are known as normal equations. Okay, so there are in all n plus 1 normal equation, and with the help of this normal equation we are going to solve it to get the value of c0, c1 up to so on cn. Okay, so this is the general form of this, and we will now consider few examples and then see what we get. So let us consider one example. Obtain a linear polynomial approximation to the function f of x equals to x cube on the interval 0, 1. Using the least square approximation. With w of x equals to 1. Okay, so this is the first example based on the theory what we have seen before. So what is given, we have to find a linear polynomial approximation, and the function given is x cube. X cube, that means it is an explicit continuous function. It is on the interval 0, 1. Okay, and as it is mentioned, w of x equals to 1. So to find the solution of this equation, what we have to do is we have to first consider a linear polynomial. Okay, so first we have to consider the general form of linear polynomial, as we have p of x equals to a naught x plus a1. Okay, this is the general form where a naught and a1 are arbitrary parameters. Okay, so first we have to take the general form of linear, because we have to find linear polynomial approximation. Now what we have is f of x equals to x cube. It is given and it is on the interval 0, 1. Okay, so we have a equals to 0, b equals to 1. So now what we are going to consider is I of, now we have to consider this constants, right, parameters. So what are the parameters? A naught comma a1. So a naught comma a1, which is equal to integration, it goes from a to b. So here we have a equals to 0, b equals to 1. So integral 0 to 1 of f of x. So what is the value of f of x? We have x cube. So x cube minus whatever the function we are assuming, that is a naught x plus a1. So it is a naught x plus a1. Okay, so whole square dx. So we have to solve this integration first to get the value of I a naught a1. Okay, so now integration 0 to 1 x raised to 6 minus 2 x cube a naught x plus a1 plus a naught x plus a1 whole square dx. Okay, so that's the first step. Then it goes to integration 0 to 1. Now what we have is x raised to 6 minus 2 a naught x raised to 4 minus 2 a1 x raised to 3 plus a naught square x square plus 2 a naught a1 x plus a1 square dx. Okay, so this is what we have. Now solving this integration, what we get is okay, so solving this, what we have x raised to 7 0 to 1 x raised to 7 upon 7 0 to 1 minus 2 a naught x raised to 5 upon 5 minus 2 a1 x raised to 4 upon 4 plus a naught square x cube upon 3 plus 2 a naught a1 x square upon 2 plus a1 square x. Okay, so now integration goes from 0 to 1 0 to 1. Okay, so now substituting the values, what we have is 1 upon 7 minus 2 a naught into 1 by 5 minus 2 a1 1 by 4 plus a naught square into 1 by 3 plus 2 a naught even 1 by 2 plus a1 square into 1. Okay, so after substituting the limiting values, so now what we get is 1 upon 7 minus 2 a naught upon 5 minus a1 upon 2 plus a naught square upon 3 plus a naught a1 plus a1 square. Okay, so this is a final value with respect to what it is, c of a naught comma a1. Okay, now to have this value minimum, what we have to do is for I a naught comma a1 to be minimum, so for I from a naught a1 to be minimum, what we need to do is find the partial derivative of I with respect to first a naught. So after this, what we get, we have to differentiate this equation with respect to a naught. So this becomes 0. So this becomes minus 2 by 5. This will be 0 because it's a with respect to a1, right? So a1 upon 2 will become 0. Now plus a naught upon a naught square by 3. So it becomes 2 by 3 a naught plus a1. Okay, so now this equation, it should be equated to 0. Now again dy with respect to the next one is a1. So what we get is 1 upon 7 0 derivative of this. So derivative of minus 2 a naught upon 5 will be equal to 0 minus a1 upon 2, it will be equal to minus 1 by 2 plus with respect to this it is again 0 with respect to a naught a1, it will become a naught plus 2a1. Okay, again we have to equate this equation with 0. Okay, so now whatever we got, these are the normal equations. These two are the normal equations. So finally what we get is 2 upon 3 a naught plus a1 equals to 2 by 5, and a naught plus 2a1 equals to 1 by 2. Okay, so we need to solve this equation. You can use any of the method you wish, like substitution, cancellation, anything, and then you have to find values of a naught and a1. Okay, so after solving this, you need to solve this. So I'm directly writing down the answer. A naught becomes 9 by 10 and a1 becomes minus 1 by 5. Okay, so whatever the required linear polynomial approximation was, it can be written as, therefore the required linear polynomial approximation is p of x equals to 9 by 10 x minus 1 by 5. Okay, so this is your required linear polynomial approximation. So what are the basic steps? First of all, you have to consider the general form of linear equation or whatever the equation you have asked. Now you have to find, see, so you'll be given some equation. It might be discrete or a explicit function, that means a continuous function. So you have to consider I of a naught even. If it's a continuous function, you have to consider integration, and if minus so it is given integral 0 to 1, whatever function is given f of x minus whatever the polynomial you have assumed, so a naught x plus a1 square. You have to find out the integration. You will get the equation of I. Okay, so we have to find the partial derivative with respect to the parameters a naught and a1 separately. You have to equate it with 0. These are your normal equations. After solving this normal equations, you will get the value of a naught, a1, whatever the parameters are, and you will get the required linear polynomial approximation. Okay, so that's your first example. So our second example is obtain the least square approximation of degree 1 and 2 for f of x equals to x raised to half or 0, 1. Okay, so again we have to find linear approximation as well as a quadratic equation. Okay, approximation for f of x equals to x raised to half. Okay, and it is given on the interval, closed interval 0, 1. Okay, so we'll find it out stepwise. That means first for n equals to 1, that means for a linear approximation, what we have is, let us consider a linear polynomial p of x which is equal to a naught x plus a1. Okay, where a naught and a1 are arbitrary parameters. In the notes, I have directly written down the equation for I c naught c1. So first of all, you need to write these sentences. Okay, so we have taken a general form of linear polynomial Again, what is given? F of x equals to x raised to half, and it is on the interval close interval 0 comma 1. Okay, here a equals to 0, b equals to 1. So again, to find I of a0 comma a1, what you have is, as it is a continuous function, there will be integration from 0 to 1. F of x is what? X raised to half minus the general equation which we have considered is a0 x plus a1. Okay, so whole square dx, and it should be minimum. Okay, so again we will solve this integration. So integration 0 to 1, square of this will become x minus 2 into x raised to half into a0 x plus a1 plus a0 x plus a1 whole square dx. Okay, so it will give you 0 to 1. So again you have to solve this part. So x minus 2 into a0 x raised to 3 by 2 minus 2a1 x raised to half plus a0 square x square plus 2a0 a1 x plus a1 square. Okay, so entire dx. Now we will find separate integration of all the terms. So what we get is integration of x is x square by 2 minus, now what is integration of x raised to 3 by 2? It is 2a0 x raised to 5 by 2 upon 5 by 2. The limits are 0 to 1, and this will be 0 to 1, minus 2a1 x raised to 3 by 2 upon 3 by 2, 0 to 1, plus a0 square x cube upon 3, again the limits are from 0 to 1, plus 2a0 a1 x square upon 2 plus a1 square x. Putting the values of the limits, what we get is, so 1 by 2 minus 2a0 into 2 by 5 minus 2a1 into 2 by 3 plus a0 square by 3 plus 2 a0 a1 upon 2 plus a1 square. Okay, so now this 2 will get cancelled. Okay, so this is what you have is I of a0 comma a1. Okay, so what we'll do is find partial differentiation with respect to a0 and a1. So deva I by deva a0 will be equal to, so derivative with respect to a0 is 0, so minus a2 a0 into 2 by 5 will be equal to, so derivative of I with respect to a0, so this will become 0, this will become minus 4 by 5. With respect to a0 it is 0, now this is plus 2 a0 upon 3, and this will become plus a1. Okay, with respect to a0, derivative of a1 square is again 0. So we got deva I upon deva a0, which is equal to minus 4 by 5 plus 2 a0 upon 3 plus a1. We have to equate it with 0. Again, deva I upon deva a0 is equal to, sorry, with respect to a1. Okay, so with respect to a1, now derivative of this is 0. Again this will be 0. Now with respect to this, it is minus 4 by 3 plus, now again with respect to a1, derivative of this is 0. Now with respect to a1, the derivative will be a naught plus derivative of a1 square will be 2a1, which is equal to 0. So what we have is two normal equation. Now we have to solve this normal equation. So what we can do is we'll just solve this. Okay, so 2a naught upon 3 plus a1 will be equal to 4 by 5, and a naught plus 2a1, which is equal to 4 by 3. So what we can do is multiply this equation 1. This is equation 1 and 2. Multiply this equation 1 with 2. So what we get is 4a naught upon 3 plus 2a1, which is equal to 8 upon 5. Okay, so now we have to subtract this equation from this. What we get is this get cancelled. So this minus this, what we have is a naught upon 3, which is equal to, now again minus a naught upon a3 will be equal to minus 4 by 15. Okay, subtracting this 2. Okay, so now what's the value of a naught? A naught will be equal to 4 by 5. Now we have to substitute this equation of a, the value of a naught in this either of the equation. So we can substitute in this one because it is quite easy. So a naught plus 2a1 equals to 4 by 3. So a naught is 4 by 5 plus 2a1 equals to 4 by 3. So 2 by 5, 2 by 3 minus 2 by 5 equals to a1. So a1 will be equal to, what's the value of a1? It will be 4 upon 15. Okay, so we got the value of a1 and a naught, and they are 4 by 15 and 4 by 5 respectively. So what we get is the linear equation will be in the form of, so 4 by 5x plus 4 by 15. So this is our required linear polynomial approximation. Okay, now similarly we will consider it for n equals to 2. So what we get is, for n equals to 2, so what we can say, consider a linear combination. So consider a quadratic polynomial approximation. So consider a quadratic polynomial approximation okay. So for this what we are going to do is, p of x will be equal to c naught plus c1x plus c2x square. This is our required quadratic polynomial approximation. Okay, so now again f of x is same, x raised to half, and it is on the interval 0 1. Okay, so I of c naught c1 c2 is again given by integration from 0 to 1. F of x is the x raised to half minus c naught plus c1x plus c2x square whole square dx. Okay, so now what we are going to do is, we can do one adjustment, that is integration 0 to 1, we will have x raised to half minus c naught in one bracket, okay, plus c1x plus c2x square and the another one whole square dx. So to find this integration, 0 to 1, so a plus b whole square, so it is a square plus 2ab plus b square. Okay, so this is what we have. So we have to find the expansion of it. So integration 0 to 1, so integration of a minus b whole square. So what we get is x raised to half square is x minus 2x raised to half c naught plus c naught square plus, now again this multiplying, what we get is 2 into x raised to half into bracket c1x plus c2x square minus this c naught into c1x plus c2x square, which is equal to integration of x is x square by 2 over 0 to 1 minus 2 into x raised to half, that is 3 by 2 upon 3 by 2 c naught 0 to 1 plus 0 plus 2 into x raised to 3 by 2 into c1x square plus c2x cube upon 3 minus c naught into c1x square by 2 plus c2x cube by 3 plus c1 square x cube upon 3 plus c2 square x cube upon 3 plus 2c1 x raised to 4 upon 4 c2. All the limits are from 0 to 1. So after substituting the limits, what we get is 1 by 2 minus 2 into 2 by 3 c naught plus 2 into 1 c1 1 square plus c2 1 by 3 minus c naught c1 into 1 by 2 plus c2 into 1 by 3 plus c1 square 1 by 3 plus c2 square 1 by 3 plus 2 c1 1 by 4, which is equal to 1 by 2 minus 4 upon 3 c naught plus 2 into c1 into 1, that is 2 c1 plus 2 upon 3 c2 minus c naught c1 upon 2 plus c naught c2 upon 6 plus c1 square upon 3 plus c2 square upon 3 plus c1 by 2. So this is the value for I of c0, c1 and c2. So the next step is what? We have to find partial derivative of I c1, c0, c1 up to so on c2 up with respect to c0. So we have to find this. So what's the value for it? Partial derivative is 0. This is minus 1 4 by 3 So partial derivative of 2c in 1 is 0. 2 upon 3 c2 is also 0. So minus c1 upon 2 plus c2 upon 6, then nothing. Okay. Now partial derivative of I c0 c1 c2 with respect to deva c1. So which is equal to, now with respect to c1, so this becomes 0, so again 2, then minus c0 upon 2, and then this becomes 0, then this is plus 2 c1 upon 3, and this becomes 0, this becomes 0. So again deva I with respect to c0 c1 c2 of deva c2, which is equal to, again this becomes 0, this becomes 0, this is 2 upon 3, this becomes 0 plus c0 upon 6, then this becomes 0, this becomes plus 2c2 upon 3. Okay, so these are the values of partial derivatives of I with respect to c0, c1 and c2. So next, these are the normal equations. So we have to equate this with 0 and we have to solve this linear equation. Therefore what we'll get the answer is, so c0 will be equal to 4 upon 15, c1 will be equal to 4 upon 5, and c2 equals to 64 by 5. So these are the values of c0, c1 and c2. So this is for today. So in the next video we will see more examples based on this. Thank you.